Before we get started, I'm Dr. Paul Gasper. I'm at the National Renewable Energy Lab. Work a lot in accelerated aging of commercial battery cells and systems, as well as modeling battery performance and degradation over time. And then I'll be talking about that. And then the other two speakers, myself and Candler Smith at NREL, had a project with Anna and Katrina from Carnegie Mellon. Dr. Ramirez-Myers, and hopefully soon Dr. Cobb at some point. If you two want to introduce yourselves quickly.
Yeah, I can start. I'm a fourth-year PhD student in the Engineering and Public Policy Department at Carnegie Mellon. Yeah, hopefully soon to be a doctor. And my research is kind of systems level analysis of different end-of-life management strategies for EV batteries.
And I'm Dr. Ramirez-Myers. I'm a postdoc in mechanical engineering at Carnegie Mellon, and my passion is just bringing down the cost of stationary batteries, whether that's through materials or technical innovation or innovative business models and energy policies.
Okay, so I'm going to spend about half of the time talking about modeling and simulation at NREL of battery energy storage systems and batteries in general. I work, a lot of this work is with Dr. Candler Smith, who's been working in battery modeling and computational modeling of batteries for a better part of 2 decades now. And then I've been at NREL for a little over 6 years working on these same topics. I do want to mention that I'm part of a group, if you're not familiar with the National Renewable Energy Lab's battery research. We do a wide variety of battery research from microwatt hour to megawatt hour scale. I, in particular, work a lot on simulation. And we have a lot of different simulation tools, from microstructural modeling and numerical generation of microstructures, chemomechanical modeling, materials and interfaces, physics-based electrochemical, thermal, and degradation modeling, empirical performance and degradation modeling. We don't always have enough data to calibrate a physics-based model, right? If you can't tear a cell apart, then you can't really calibrate a physics-based model. So in that case, we use empirical approaches for modeling performance in lifetime. And then we also do thermal and mechanical abuse modeling. So basically, as detailed as you would like to get in terms of how you're modeling your battery, we can model the expansion and contraction of individual positive electrode particles or model systems with empirical approaches. If you don't think a lot about battery degradation and safety, I'm here to help because I do. But the main takeaway is that degradation, reliability, safety are complicated and interrelated. So here's this now classic figure by Christoph Berkel, which shows all the different not all, but most of the different possible degradation mechanisms that can occur in a traditional lithium-ion battery. And right, these have interrelated effects on like safety, reliability, and performance that makes degradation worth paying attention to. And a very hard part for modeling them or understanding them is that they're not directly observable necessarily from the electrochemical data. And I just want to harp on this is a current problem. So this is testing data from an accelerated aging test conducted at NREL of a tier 1 OEM battery cell operating within its manufacturer recommended operating limits, and you still get an extremely wide variety of degradation behaviors and failure modes for even a single battery type. So right, this is, when you have degradation varying this much, it's definitely worth having a model for, worth paying attention to. So there's several challenges for battery monitoring and lifetime related to performance and durability. We work on all of these topics. There's diagnostics, which is, right, if you have like a state of health curve, it's figuring out where you're at on that state of health curve. In actual field operation, right, we don't necessarily model state of health. Or we don't necessarily stop the system's operation to perform a state of health check. We want to be able to diagnose it rapidly. We're not going to talk about that today, but we do work on this problem. Then there's if you know where you are, you want to do prognosis. So you say, well, what happens if I continue operating the battery in the same way? What's going to happen to it? We usually use accelerated aging data to calibrate models for that. And then finally, we have decision making, which is if I have a model that can predict the future with some uncertainty, then I can make some sort of decisions about how I want to change that trajectory, right? To extend its lifetime, to generate more revenue, whatever, right? I have some sort of model that predicts the future, and I can use that to make decisions. So we're going to go over battery health prediction. The main challenge for that is we normally calibrate models with lab testing, right? At some point, every cell has lab testing, even if that's just like data sheet level information. Or if you're ordering a very large amount of cells from a cell supplier, you're going to get a bunch of testing data from that cell supplier, of like temperature, stability, calendar aging, cycle aging at different conditions. And then you're trying to use that to calibrate a model and set expectations for real world operating behavior. So when we look at NREL in specific, does a lot of life testing of commercial lithium-ion cells. So this is an example from publication where it's showing data from different accelerated aging tests conducted at NREL, as well as some of the different performance metrics of those cells over time. So we perform these tests, perform all the analysis of the electrochemical data. And then we use that to identify models. And this is a fairly complicated activity. The main problem is that you have a bunch of different behaviors. So for example, here we have calendar aging on the left, calendar aging at different temperatures. So loss of capacity over time due to storage temperature. It also varies with the storage state of charge. And then you have cycling degradation, which is an additional to that calendar fade. That might be a function of your charging or discharging rates, your average operating state of charge, or your operating depth of discharge. So there's a wide variety of trends here, and we're trying to find one function that predicts relative discharge capacity as a function of some small set of optimizable parameters and all of those different input variables, right? How many cycles I do, how long it's been since beginning of life, operating temperature, operating state of charge, all these different variables. So to do that, we use a combination of statistical model identification and machine learning methods. So we have a bi-level optimization scheme that allows us to identify curves to fit each individual battery test with the fewest number of total degrees of freedom, which is a good way to regularize your model, make it hopefully more reliable. If the model has too many degrees of freedom, you end up being overfit. You don't get like nice trends, of like the degradation rate versus temperature and stuff like that. And then we use a machine learning technique called symbolic regression to find algebraic equations that predict the degradation rate as a function of its operating condition. So temperature, state of charge, depth of discharge. And then this is a bit of machine learning and statistical modeling. So we use a lot of simulation to make sure that our models are reliable across any possible operating conditions. And that ends up with one model that fits every single capacity fade or resistance growth trajectory in a data set. You can see the fits are quite accurate, usually within less than 1% error for high quality battery test data. And so we have a single equation that's fitting all of these curves simultaneously. So we can describe a wide variety of behaviors with a single model. And we take that model, fit to accelerated aging data, and do a little bit of math to convert it into a state space model so that we can predict degradation during the real world. Right? If we look at one of these test conditions in the lab, it's at a constant temperature and a constant state of charge, which is not how we use batteries in the real world, right? The ambient temperature is changing, the state of charge is constantly changing. Sometimes it's resting, sometimes it's being operated. So in order to do that, we do a little bit of math. We take the model that's a function of time and invert it, so that's a function of state. The common thing, an easy explanation for this is that the state of the battery isn't a function of time, right? if I take a battery, if I take this battery here and I put it in a freezer, then it should be a completely flat line. And then I take it out of the freezer, it should go back to degrading, right? So you need to make your function a function of state rather than a function of time. And then we linearize that function so that we can, during any given day or any given cycle, the degradation is effectively linear. And then we run a simulation that steps through time and accumulates those state changes. And then we can use that to calibrate calibrate our models and evaluate real world degradation behaviors. So here's an example of taking public data from Tesla info, which is real world Tesla. In this case, it's Model 3. I believe this is the Model 3 long range data. And then calibrate our model to that publicly available data, and we can see that the model is both matching the data and predicting a pretty believable extrapolation from the real world electric vehicle degradation. Obviously, the real world is always going to have more variance than our model, just because it's the real world, right? There's battery failures and other things we're not accounting for. And these methods are available fully open source at github.com/nrel/blastlight. And this blastlight package has a bunch of models identified for different commercially produced lithium-ion batteries. So each one of these models is like time, cycle throughput, state of charge, and temperature dependent, if not also dependent on charging rate or discharging rate or depth of discharge. So you can use one of these existing models to model a commercial battery and understand like how changing the depth of discharge might affect its expected operating lifetime. And again, fully open source. So please check it out if you're interested in that. We also do physics-based electrochemical modeling. Everything I've talked about so far is empirical, right? So I'm basically fitting an equation to a bunch of the performance metrics. But we also do physics-based electrochemical modeling with degradation, and this will be some sort of physics-based electrochemical model solving mass transport, charge transport, and other conservation equations. And that will predict the spatial and temporal variation of lithium concentration in the solid and liquid phases within the battery as it's operating. And then we also can incorporate degradation side reactions into these models. This is an example of one of these physics-based electrochemical models matching rate capability data. This is a plot predicting lithium plating. So this is the anode potential at the separator relative to lithium. So when you're below 0, you're in a thermodynamically favorable region to plate lithium. And then we can incorporate common degradation mechanisms into those models to simulate the evolution of those electrodes in a physics-based model over their lifetime. So finally, if we have models of lifetime, how can we optimize our battery system? Right. Well, we can turn lifetime metrics into cost metrics. So one very simple one, sorry, we can optimize the life of a battery, given a depth of discharge and a temperature. Batteries are very boring. They often tell you that the way you can get the longest lifetime is if you just don't use it. But that's obviously not very useful. We're actually more interested in something like a cost factor, like how many replacements, if I actually do use this battery, how many replacements will I need given a certain operating window to meet a system lifetime? So we can make a simple like cost factor estimate to say, well, if I want a system that has 1 megawatt-hour of capacity at year 20, how big will I have to build my initial system, and how many times may I have to replace it to meet that lifetime requirement? And so I call that a cost factor. This is a very simplistic estimate because it's not accounting for stuff like the discount rate or interest over time. It allows you to just make a simple guess of how you might need to size a battery system to meet like a 20-year lifetime expectation, and how many replacements you might need to get. But we can do better than that. We can put battery degradation models and true techno-economic models with potentially with like cost optimization or long-term techno-economics baked into the models. NREL has a bunch of publicly available tools to do that. There's REOPT and the system advisor model are techno-economic models. REOPT performs optimization of sizing and dispatch of systems as well. The system advisor model also optimizes battery dispatch during its simulations, if you would like that. And so here's an example of putting a battery degradation model into REOPT. One of the challenges of battery degradation is there's different maintenance strategies for batteries over time, which incur different costs. So one of those possible maintenance strategies is replacement, which is if you degrade the battery to its end of life, whatever that threshold is, you have to replace the whole system. And then there's also augmentation, which is as you lose capacity, you just buy a few new batteries to replace the lost power, but you're not actually getting rid of all the batteries as they, once they hit end of life. And that kind of gives you a conservative and optimistic baseline, optimistic costs, cumulative maintenance costs incurred by battery degradation. And we find these predicted costs are often lower than baseline, some of our baseline assumptions, such as assuming replacement every 10 years. And these models give us some interesting results. So here's a bunch of different metrics, like the power of the energy storage system and the energy capacity, as well as like how much money it saves on different utility, energy, and demand charges. So on the left here are a bunch of systems where we fixed the size, and then on the right are two systems where we've allowed the size to vary. And when we have a degradation model, it actually builds a much bigger battery, but then it uses that battery a lot more to generate a lot more revenue, make a lot more energy savings. When we fix the size of the battery, it uses that battery less to avoid degradation costs. And we can use these models to ask questions, for instance, like what happens if we have an annual minimum average state of charge to make sure that we always have energy available, and provide a dollar value on that. So this is an example simulation where if we force the model to have an annual 80% minimum average state of charge, so there's almost always energy available in that battery, it incurs an additional, up to 7% of the capital cost in long-term maintenance. So with that, I'm going to pass it to Anna to present on how we can use this as well as a further techno-economic models to look at the techno-economics of second use.
Okay, I'm just going to hop right in because I think I might end up going pretty close to time. Let me see. Okay, thumbs up from somebody that my screen. Okay, great. Thank you, Katrina. Okay, so thanks, Paul, for explaining one of the really important models we ended up using in this work, which is blast light. I'm presenting some research today that was a collaborative effort across some of my colleagues at Carnegie Mellon, Paul and Candler, who Paul also mentioned at NREL, and Bryant Polson at Argonne National Lab. And the title of my presentation is Why Lithium Iron Phosphate Batteries Have Greater Second Life Potential Than Nickel Cobalt Batteries. So as many people on this call have probably thought about or worried about or been really excited about, we recognize that electric vehicle retirement is a rapidly approaching and growing challenge. This plot shows the number of electric vehicles that we project to retire over the next several decades, separated out by the age of the vehicle. And from this plot, we're seeing that around like the mid to late 2030s, we might have over 1 million electric vehicles retiring or coming offline every year. And part of figuring out this whole aftermarket for electric vehicles will be figuring out what to do with the lithium-ion battery packs that are inside of these vehicles. So right now, there are kind of three main pathways that seem like viable options for what to do with these lithium-ion batteries when they're no longer suitable for use in an electric vehicle. One option is repurposing them for a second life in some other application than a traditional electric vehicle. We're going to focus today on stationary storage applications. Another option is to recycle them either directly after their use in an electric vehicle or after they've been used in a second life. And the third option, which I admittedly know the least about, but would be interested to learn more, is potentially disposing of them in a way that's, responsible and safe in some sort of hazardous waste facility. But today I'll focus on repurposing and recycling, although most of our analysis is about repurposing. But in addition to just looking into repurposing, we were really interested in understanding the dynamics between recyclers and repurposers and how batteries are going to get directed down one pathway versus the other. So part of the reason that we don't know the exact answer to that question of like where batteries are going to go is because the economics of repurposing are still pretty uncertain. And I'm going to, on this slide, go through like one source of uncertainty, but there are so many others that kind of motivated this work that I'm going to talk through one. So in 2015, researchers at NREL published this very comprehensive report on the techno-economics of second life batteries. And this report included an open source repurposing cost calculator that basically estimated the cost of operating a facility that tests and evaluates used batteries for second life applications. They looked at like testing modules specifically for repurposing, didn't look at pack level. And since the study was published, it's received hundreds of citations. I think part of that was due to this cost calculator, which is a really useful tool for people who are trying to look at the economics of different types of second life applications. But in 2018, the standard was published by the Underwriters Laboratory UL, which was the UL 1974 standard for repurposing facilities. So this is a facility level certification that you can get as a repurposer if you are following the steps outlined in the UL 1974 standard for testing and evaluating batteries. So one of the kind of beginning questions motivating our work was, well, if we incorporate the testing steps outlined in UL 1974 into the repurposing cost model, how is that going to change the costs of repurposing? So that leads me to our research questions, and there's an asterisk here because there were two deliverables from this work. One is a white paper and one is a journal article, and today I'm going to be kind of focused on what we cover in the journal article, though I'll note that in the white paper, it's a little bit more expansive and we cover some additional topics. So our first research question was, under what conditions can second life stationary storage systems be economically competitive with new stationary storage systems? And our second question is, under what conditions is repurposing electric vehicle batteries for a second life economically competitive with recycling them? So to answer these research questions, we used both some pre-existing models like Blast Light and some new models that we made specifically for this research project. So I'll start with one of our new models. As I alluded to earlier, we did want to come up with an updated repurposing cost model that both incorporated the steps outlined in the UL 1974 standard, and also we wanted to see how costs compared for repurposing at the pack versus the module level. So then we also used Blast Light to predict battery degradation across the first and second lives of the EV battery. And this enabled us to figure out, okay, across different factors that were varying, how long will batteries last in a second life. And then we use the outputs of both of these models as inputs to an economic model that we have, which I'll talk more about on the next slide, but that essentially allows us to answer that first research question of how the economics compare for new energy storage systems and second life ones. And then lastly, we use the Everbat model, which is a big open source industrial scale battery recycling model out of Argonne National Lab that estimates costs and revenues of recycling different battery chemistries with different recycling processes. And we use that to look at the economics of recycling. Okay, so now I will talk through our economic model in a little bit more detail. The output of this model is what we call a break-even acquisition price for used EV batteries. And rather than trying to explain that up front, I'm going to show how we calculate it, which I think is the best explanation for what this value means. So we start by setting the annualized cost of a new battery energy storage system equal to that of a second life battery energy storage system, where the annualized cost is equal to the system cost times the capital recovery factor. And the capital recovery factor is a function of discount rate and system lifetime. This discount rate is something that we set exogenously, so we know what it is. The system lifetime is what we get from Blast Light. On the system cost side, it looks a little bit different for a new battery energy storage system than a second life one. I think we all know what's needed for a new battery energy storage system. And basically we can find, I just heard a loud noise. I hope nobody else heard that. For the new battery energy storage system, we can find basically the costs of all of the components that are needed from the literature or from other data sources. And then for the second life battery energy storage system, there's separate things that we'll need to know, one of which is the cost of repurposing, and that's what we get via our repurposing cost model that we made. And the second item is the cost of used EV batteries. And this is kind of unknown at this point. There are like online markets that talk about this, but we don't really know what this value is. And so this is what we're referring to as the break-even acquisition price. One other way of saying this is that this value represents the maximum amount that a second life company would be willing to pay for a used EV battery to manufacture second life battery energy storage systems at the same annualized cost as new battery energy storage systems, which is a little bit of a mouthful, but that is how we're defining it. And then for recycling, we use the Everbet model to estimate the revenues and costs associated with different battery chemistries and recycling processes to come up with the break-even acquisition price of used EV batteries for recyclers. Okay, so there's a lot of different factors that are going to influence how long batteries last in second life. We look at the cathode chemistry of the battery, how long it spends in first life, how intensely it's used in first life. Here we're looking, our metric for that is vehicle distance traveled, which we look at as a function of vehicle age from National Household Travel Survey data, and we vary at plus or minus 15% to set up our bounds. And then we look at 6 different second life applications that vary across the characteristics that are listed here. And then we also look at what we call the derating factor, or derating the second life system, basically oversizing it such that what was once a 100% depth of discharge cycle is now reduced to something smaller. And we look at a range of derating factors from 1 to 5, where at a derating factor of 5, a 100% depth of discharge cycle becomes a 20% depth of discharge cycle. Okay, so now I will get into our results. I apologize if I'm going really fast. I brought up this diagram again just to kind of map out where we're going, because there's some intermediate results that I'll talk about. I'll start with the estimates for cost of repurposing from our updated cost model, and then I will get into the Blast Light results showing how second life varies across different factors. And then I'll get to the results of our economic model, looking at the break-even acquisition price of used batteries for second life companies. And then lastly, we'll compare that to the break-even acquisition price for recyclers. So starting with our cost results, our big takeaway is that pack level repurposing is significantly cheaper than module level. And ultimately, well, I'll explain this plot first. We show for each like repurposing level, pack or module, what the repurposing cost is that we estimate in dollars per kilowatt hour. And then we break down these costs into these different categories. And yeah, the ultimate reason driving this difference between pack and module level repurposing costs is that we find testing the same amount of kilowatt hours worth of modules compared to packs is much more expensive. There's a couple of things that play into that. One of them is how the tests are written in the UL 1974 standard, and the other is kind of the pricing of cyclers and how that ends up working out for modules versus packs. Getting into the lifetime results, this is a sample plot. I will show a version of this plot for all of our applications in a second. But here I'm showing the second life duration or the second life of the different batteries as a function of their chemistry and first life cutoff, as well as the derating factor that we choose in second life. And you can see that for the nickel cobalt chemistries, increasing this derating factor increases their second life duration, which is perhaps no surprise because if you're cycling them less intensely, they're going to last longer. But you can see that for LFP, we don't find that any derating is really necessary to increase system lifetime. And I'll note that you can see these lifetimes increasing up to a cap. We impose a 30-year limit across the whole simulation, so the battery's first and second life. We just have less confidence about what happens after 30 years, so that's why you see them flatten out. Okay, and then this is the same plot, but for all of the different applications that we look at. And in general, we can see that derating really improves lifetime for the nickel cobalt batteries. And especially as we get into the more like higher EFCs per year applications, the derating is making like even more of a difference. So you might think we should just derate forever, but there is a trade-off to derating, which is that it increases system cost. So this plot on the right is showing break-even acquisition price as a function of derating factor. And you can see that for the nickel cobalt chemistries, it's got a little bit of a concave shape. I've highlighted the maximum break-even acquisition prices as stars. And the reason for that is that, as I said, derating increases system costs because, it increases system costs through like having a larger enclosure, which is more expensive and needing to buy more cabling. But it also means that you're having to purchase more EV batteries to go into your system, so you can pay less for any one of them, which lowers your break-even acquisition price. So if we look across all of our applications, we can see that to maximize break-even acquisition price for the nickel cobalt chemistries, we often need to like substantially derate the systems, less so for LFP. Okay, so I'm going to show these results in one more format where I don't show things as a function of derating factor, and I'm just going to take the maximum break-even acquisition price from these plots and just show that on its own. Okay, so starting with LFP, this plot shows the break-even acquisition price across all of our different applications, and then the error bars represent the different first life conditions that we simulated. And you can see that we get like in the tens of dollars per kilowatt hour purchase prices for LFP. But if we compare this to the recycling break-even acquisition price that we get from Everbat, that's actually a negative number, which means that recyclers currently would have to be paid money to accept and recycle LFP. And this suggests that repurposing in general is going to be favorable from an economic perspective to recycling for LFP. Next, we'll look at NCA. These results look pretty different, and this is because of NCA's relatively smaller lifetime, more required derating in second life. Most of the break-even acquisition prices are negative or are at least sometimes negative. But if we look at the recycling break-even acquisition price, it is always positive, even if it's kind of small in some cases. And so this indicates to us that in general, you're going to want to recycle NCA rather than repurpose it, unless it's a very cycling, not intense application. And then lastly, NMC, these results are the most varied. We see some applications that show positive break-even acquisition prices, some that are negative, and recycling also looks positive. So NMC, we recommend to some degree, like thinking more about the decision that's being made and sorting based on the state of health of the battery after its first life and the second life application that it's expected to go into. Okay, let me check my time. Okay, so I'll wrap this up really quick. I kind of said this on the last slide, but our main conclusion is in general, it's going to make sense to repurpose LFP, recycle NCA, and sort NMC into recycling or repurposing based on state of health and second life application. I'll just note that there are some uncertainties that remain for the repurposing industry. For sure, this does not highlight all of them, but they come in the form of both risks and opportunities. Risks being potential saturation of kind of the applications that Second Life makes sense for, especially as more electric vehicles retire. That's something we get into in the white paper a little bit. There's also consumer perceptions of safety, but legitimate like safety risks to using Second Life batteries. On the opportunity side, we have the evolution of rapid diagnostic technology. There's a lot of companies working on this, and I think a lot of people recognize that it would be useful to be able to very quickly assess what the state of health is for a battery. And then lastly, there's the potential for UL standards to evolve, and also for Second Life companies to achieve the UL standards, which may increase consumer confidence in their products. Okay, that was fast, but yes, thank you for listening. Thank you to everybody who collaborated on this project, including Paul and Katrina, who's also on the call, as well as our funding sources and all the people that helped us with the research. So.